involved a series of rocks that contained unusual conical structures, being known as shatter cones. These rocks, when found in an area which was never the site of nuclear weapons testing, can only indicate one thing: that they formed long ago during an asteroid or comet impact so large that it caused underlying rock to experience upwards of 250,000 psi. This spider-like spider impact crater structure marked the center of an impact crater, which would become known as Spider Crater. Only part of its crater rim is still visible today, most notably on its northwest, with this feature measuring 13 kilometers long and 11 kilometers wide. But when exactly did this feature form? Cryogenian period. One clue involves another highly unusual rock type which you would not expect to see in a region which today frequently exceeds temperature of 35 to 40 degrees Celsius during the summer: a type of rock known as tillite. Tillite forms when thick glaciers deposit a layer of till due to their motion, containing numerous angular fragments which combine to form a sedimentary rock. This rock unit, known as the Walsh Till, dates to a time between 655 and 632 million years ago, when this part of Australia was located in the northern hemisphere at about 25 degrees north. Despite being located close to the tropics, this marked a time when more than 60% of the planet was covered by glaciers largely above 25 degrees latitude, and average world temperatures may have been 10 degrees Celsius. The reason I am mentioning about the Walsh Till is that it seemingly overlays a portion of the impact crater, suggesting that the crater is older than the Marinoan glaciation. As for its maximum age, that would be around 900 million years old, placing Spider Crater as somewhere between 632 and 900 million years old. While no exact dates exist, a current best guess suggests that it formed approximately 700 million years ago during the early Cryogenian period. This crater formed when a 970-meter or 3,182-foot wide asteroid, impactor details presumably from the main asteroid belt, was on a collision course with Earth. As it accelerated towards our largely glacier-covered planet undergoing to the Sturtian glaciation, it reached a speed of 17 kilometers per second or 38,000 miles per hour. Reached the upper atmosphere at a shallow angle of 25 degrees. It began to partially burn up but largely remained intact due to its massive size. Then, 14 seconds later, it impacted the surface, generating a tremendous explosion equivalent in energy to the detonation of 55.4 billion tons of TNT. After a spider legs formation, large cavity in the ground was excavated which had a slightly oblong shape. Some material at the edge of the crater became temporarily fluidized, quickly moving towards its center. Simultaneously, this combined with a rarefaction wave which unloaded compressed rock beneath the crater floor, causing the rock in the center of the crater to rapidly rebound upwards. As a result, an 800-meter-wide block of material was thrust upwards, forming the center dome of a complex impact crater. With all of this occurring in a mere 30 seconds after the impact, numerous thrust faults in a radial pattern around the center were also created. These thrust faults were largely composed of a very hard rock unit known as Pentecost sandstone, which was composed of quartzite-rich sandstone. This made that layer of uplifted sandstone harder and more resistant than the underlying two layers of siltstone and non-quartzite-rich sandstone. Thus, over time, while much of the adjacent layers not capped by the Pentecost sandstone eroded away, the pieces with the quartzite-rich sandstone protected underlying rock, forming prominent white ridges. And these ridges, representing the top exposure of thrust faults, are what formed the legs of the Spider impact crater. As a final note, I would like to thank my new patron Thomas Kent for supporting this channel.